Swayam Prabha. Digital India. Educated India.
Good afternoon, everyone. It gives me immense pleasure to introduce a truly inspiring individual, Professor Sunetra Ramanan. With many years of expertise, she has completed her PhD in physics in Ohio State University. Her areas of interest include nuclear structure, quantum dynamics, and much more. She is known not only for her professional accomplishments, but also for the kindness and wisdom she brings into every space she enters. Professor Sunetra Ramanan has been a guiding light and a source of inspiration to many. Her presence here today elevates this occasion, and we are truly privileged to have her with us. Thank you.
Thank you very much. It was a very flattering introduction. So maybe that I should. Is there any part of the board here or? Oh, then I can bring it down. Okay, all right. I thought this was going to be a bigger board. Anyway, so what I'm going to do today is talk to you a little bit about how computers are used in mainstream physics. Okay, so up until now, you have sort of learned physics separately, mathematics separately, computer science perhaps, some of you biology, but all this division does not really make too much sense. We apply different tools from different areas. Okay, for example, I work in theoretical physics, and what I do is mostly application of mathematics at different levels. Okay, and of course I also program, because what is important for a theoretical physicist these days, or in fact all of science, is to be able to do numerical simulations. Okay, they are in fact numerical simulations are so important that experimentalists first try the feasibility of an experiment by simulating it on a computer before they ask for funding. Okay, so therefore this is so what I want to tell you today is to how to get reliable results using a computer. So in some sense I do use programming. I program in C, C++, Python, Fortran 90. It just doesn't matter what language it is, because at the end of the day, it's only logic and what you need to do. Okay? So, what I will tell today is about the limitations you have on a computer. Okay? The first computer perhaps the first computer I saw was something that took nearly 1 hour to boot. We had it in our house because my father's office gave it to us, okay, for his work. So he was kind and he allowed us to play some video games on it. But that thing took 1 hour to boot. It will be connected to our TV. There was one TV only. There were no cell phones. And you had this TV, it will boot. After it booted, you will play on it for perhaps some 45 minutes to an hour, when the electricity charges will be high enough that we switch off the whole thing and go out and play. That's what we did. Okay. From there, of course, since my father was involved in an office where he was the one who was computer savvy, so then we saw evolution. So the first one was, at least one we had at home, was a Commodore 64. Then it improved. Okay, so we really saw PC and other things. And when I did my PhD, the first machine I had a RAM of 256 MB. And when that changed, when that changed to a GB, I was so excited. The first laptop I had 512 MB. It was slower than my desktop. Okay, and nowadays our cell phones are faster than that. Okay, however, you may wonder, what limitations am I talking about? The limitations I'm talking about is in the word length, because when you store and use a computer, you want to store data. It could be characters, it could be real numbers, it could be integers, because these are the things you will work with. Okay, so therefore there is an inherent limitation. So every chip that you use has a word length defined, right? So therefore you may have something, for example, most chips that we have, as well as languages, allow for a word length of 32 bits. Okay, 32 bytes would have been good, but still that is small. All right, so 32 bits. All right, and this is what is typically used to store an integer, real number, and so on. You can ask for more. Okay, you can ask for more. You ask for more by, you can ask for more or sometimes even less if you want to optimize. Okay, you may ask for something 1/2 of this. You may ask for something which is double of this. But that's about it. There's nothing more you can do. All right. So within this, you have to store, operate, and get results of anything that makes sense. Okay, and you also have to convince others that what you have is not some random approximation, but this is the approximation I have used and this is the error in this approximation. Only then is any result even meaningful. Without errors, it makes no sense. Okay, so now with 32 bits, let's ask what are the things we want to store. We want to store, let's say, integers. Okay, now 10 to the 23, that's the order of Avogadro number. Can this be stored on a computer as an integer? The answer is no, it can't. What is the biggest integer you can store? No, 10 to the 9. 10 to the 9, maybe with some optimization and maybe some modern language, you may be able to say store 10 to the 15. I don't believe so. I think 10 to the 9 is all you can do. All right. So why so? Because you have, say, 32 bits, unless you're able to change that. Okay. With 32 bits, you want to store an integer, which can be positive or negative. So 1 bit goes into storing a sign, because a bit is basically 1 or 0. Correct? So 1 bit goes into storing the sign of this number. Let me pull my cover this because I'm not able to see you people there. Yeah. So 1 bit goes into storing the sign. All right. So you have 1 bit for the sign. So you have 31 bits. That's it. Okay. Which means you have 31 ones and zeros. So how many numbers can you have? 2 power 31. That is of order 10 to the 9. I don't care what, how much into 10 to the 9, but that's roughly the number. Which means if I do a simple multiplication of 2 to the 5 into 2 to the 5, I'm done. Okay, this is called an overflow error. All right, and if you have when you have an overflow error, again it depends on the compiler. These things are evolving. Every day you have compilers throwing much more information at you than previously. But you could get anything. If the compiler is smart enough, you will have a compiler error or a compiler warning. Either because there's no error, there's no syntax error. You may have a compiler warning. Or you may just get junk if you ignore the warning or somehow turn it off because you're lazy, you don't want all these things built on your screen. Then you may turn it off and say everything is right with my code, I'm just going to run it. Then you will get complete nonsense. Okay. The other thing that comes with a computer is that the math on the computer, something that you may not even know, because I'm sure all of you program with Python. So, sorry? And Java. So let me ask you, you tell me the answer and I will tell you how I will do it. Suppose I have a number 1 by 3. You know how to do this. You know the answer. It's certainly not 0. But if I do an integer approximation, it is 0. Correct? So how does Python give you this? What answer will it give you? Yes. But if I did this with Fortran or C or C++, just as a 1 integer divided by 3 integer, I'll get a nice 0. Because the answer is also stored as an integer. The only way to convert it is to make it a 1 point or a 3 point. So usually, old-fashioned programmers like me will write this as 1 point, 3 point. Some things that modern compilers don't necessarily need it. Perhaps modern programming languages may not necessarily need it. But this is a discipline that came after years of debugging programs because something failed. For example, if I have to calculate volume, okay, of a cylinder, this will give me a 0. Because if I say 1 by 3, suppose I write my volume as 1 by 3 into pi into r square. This will fail, it will give me a 0. On the other hand, pi r square h, right? So suppose I do pi r square h divided by 3, this will work because the numerator are all real numbers. So automatically the answer will be a real number. Okay, so there are basically the math that you do in real life is very different from the math you do on a computer, and this is something one has to appreciate, because at the end of the day, these are the devices you use to do science. Okay, so now this is the story with integers, right? What about real numbers? So how do you represent integers now? On a computer, it's going to be all binary. Correct? So instead of it in a decimal system, you have expansion in in powers of 10. In binary, you have expansion in powers of 2. Correct? So any integer, which I say, if I call that integer n1, is going to be some a0 plus a1 plus a2, 2 square, plus etc. Because I have finite limit, there is an upper bound, which is A31, 2 power 31. That's it. Okay, and that is the reason I cannot have any more than something of order 2 to the 9. All right, and you all know how to do this in binary. Okay, now what about real numbers? Yeah. Correct. That's how it works. A real number. That's how it is always. So what will differ, for example, across languages is perhaps the number of bits. So they may trade 1 bit here, 1 bit there, or even that is standardized. You have this IEEE standards, okay, which make sure that across all programming languages, you get the same answer. You have the same optimization, because no programming language should fall behind something else. Okay, so these things are always true. So in general, real numbers, you are absolutely correct. So if I have a real number, let me call, so this is an integer, right? So what do I write for a real number? Shall I say some a real number a? Oh no, I'm using it for the coefficient. Give me some other number. K, I like k. So let's put k, real number k. Okay, so a real number k is usually written as some sign, because there is a sign in this real number. So let's put plus or minus. We don't know what it is going to be. Then you have a mantissa into an exponent. If it is decimal, it will be 10 raised to something. Here it will be 2 raised to some exponent, which I will call m. All right. Now, the standards will be such that you optimize the best between the mantissa, the exponent, and the sign. Sign, anyway, you will need 1 bit. Okay, you could have a convention, for example. So the sign will always consume 1 bit. Okay, so you could say that you could have some definition, right? 0 implies positive, 1 implies negative. This is a convention. Okay, I'm defining it here. It could be IEEE, could be the other way around, because in some cases 1 is 0 is success, 1 is failure, or something like that, but really it doesn't matter. It's a convention. 1 bit is consumed there. Okay, yeah.
In the N representation equation, I think it should be only till 2 power 30, A30 2 power 30, because
Why? Oh, because you're right. You're right. Yeah, you will exceed. No, because you're right, because I have this guy. A naught. I can absolutely store only 31 pieces of information. You are right, absolutely. Correct. So,
again, this entire representation can max give a number only till 2 power 31 minus 1. It won't give the 2 power 31.
yeah, that's why I didn't include it.
Yeah,
So, for example, what I should have done is plus minus. There is a sign. I didn't include the sign, isn't it? No.
Okay, cool. Okay, I got it.
Yeah. No. Sorry, what was your question? I thought this was it. What was he?
I said you can store.
No, I didn't understand maybe what your problem was. I think you answered it, but I just want to know what it was.
What I'm saying is that you keep adding powers of 2 starting from 0. Then if you add, like, if it's sigma 2 to the I from 0 to like n, then it's 2 power n plus 1 minus 1.
Yes, absolutely correct.
Then if the number
No.
31.
No. That's not true.
That's for positive integers.
Yes,
But for negative integers, you can store
2 power n minus 1.
but there's no negative.
There's no negative sign. So you need that sign information anyway, irrespective. So if you want to, okay, I got your question. So if you want to get that extra bit also, and you are sure that that number is only going to be positive, then you declare it as a positive integer. Yeah, you can get that. So there is some definition, I think it is called some, I forget. There is a way to specify that it's a positive number always, so that you don't have to worry about that information. For example, here also, so in the mantissa, okay, unsigned, yeah, that's the name, unsigned integer. If you say unsigned, then it assumes that you don't care about the sign, you give that bit. Okay, for example, if it is a logical thing, then you don't need it. Okay, so now what about the mantissa? The mantissa too is an expansion. Okay, now there are conventions which will give you a little extra bit. For example, you could have one convention where you have an expansion in, say, I going from 1 all the way to some, what shall I call it, some capital N, a minus I 2 raised to I. Okay, therefore the number will be 0 point something. Correct? That's how it is going to be stored. Now I can also have a convention where it starts with 0. Sorry? A minus I is because I forgot the I there. 2 minus I. Because I want to do inverse power. Right? So I should have put the 2 minus I. There you go. So therefore I want to have the same symbol. That's all. Okay? So that if it is 1 by 2, it is A minus 1. 1 by 2 square, A minus 2. Alright? So therefore, if I do this, okay, as opposed to, for example, this is 1, another convention might allow me to go from 0 to n, a, well, or let me call it b minus I 2 raised to minus I. Now I will get one extra bit here, and I can always force my extra bit to be such that, to optimize that extra bit, I may always say B0 is 1. Because after all, you will have a significant bit somewhere. And that significant bit is 1. And you can move this guy across. So you can always write your number as 1 point something into some exponent. So these are different ways to optimize to get one extra bit here or there. But you see that there is a main constraint, which is the fact that you have 32 bits. You cannot go bypass that. Okay? At best, you may get 64. But what is 64 or 32 amongst all the numbers you have? Yeah.
Yes, I have a question. So, ma'am, during theoretical physics, you said you run programs using code lab. So, ma'am, why don't you use high-level languages like Python, Java?
Yes, we do. We do. However, I have many of my students knowing Python. I too can program in Python. But sometimes what happens in a code might be more efficient when you write it in C, C++ or Fortran. Why so? Because in Python, it's a high-level language where the compilation is done at the end of every line. So precisely. It's like Mathematica, okay? Or Maple or anything like that, where you hit return and it executes it. Whereas if you write a more conventional program like C, C++ or any Fortran, Fortran was actually written for scientific purpose, okay? Even C and C++ are also all right, great programming languages. Maybe does not have all the features of Fortran, okay? However, in all these languages, it has this following common point that you write your code. So you have your logic, you write your execute your logic, you translate just once, and it executes. You may have optimization in both, but for very long programs which take hours to run, these win over Python. That's all.
Python also have a
Yeah, it has. But you do the translation once, right? You don't do the translation once, isn't it? It's an interpreter. It is done line by line. Certainly there is a compiler. Okay, so as you do, you can also do the following, which is write your program and then run it, Python, whatever, some file.py. Even then the translation happens line by line. There are optimizations, okay? But this wins time-wise on that. Here also it shows the errors. Here also it shows errors. There is nothing that doesn't work. And in the end, I'm sure that if you have because Python is now everywhere, it's just a matter of a few years before it can be as efficient as these.
Is it time efficiency? Is like what
Time efficiency. Time efficiency as well as, see also maybe what I'm saying is a little outdated, so I will say it carefully. For example, if I have to write, in Python you have a lot of packages which you can use. Modules. Whereas here with these languages, there are, usually for linear algebra you use packages. There is no other way of doing it efficiently. But for everything else, you develop the algorithm. When you develop the algorithm, you know the nitty-gritties and you can tweak it, you can make it very efficient. You can optimize it. Okay? So this is just a matter of time. When I started learning, this might have been very different compared to what it is now. The RAMs have changed. Everything has changed. Okay?
Can't you define a function in Python also?
Of course you can. Absolutely you can. It's only the way in which it compiles. So it gives you a little more optimization at this point. But this can change. And I'm not even going to say that this is how it is going to be. All right? Someone else had a problem somewhere. Yeah.
What I wanted to see was also back post my graduate class software engineering. So I learned a little bit from them. They tell me always that Python is very inefficient with handling memory. Right? And the way it gives out memory addresses is like kind of random. And to access those things.
Okay, this I didn't know. Today I learned something from you. Absolutely. Okay. So because in C and C++, the memory is contiguous, or rather, you always want to program, when you want to write a program which is efficient, you want contiguous memory so that it goes one after the other. Absolutely. Okay, so there he is giving you one more point. I didn't know this, but thanks. That's a good thing to know. Okay, so the memory allocation. So normally in a program, what do you have? You declare variables. Okay, so when you have variables, you want memory to be located one right next to each other. So it's easy to access, it's more efficient. Suppose I have a list with 10 elements. I want these 10 elements to come one after the other. I cannot, I didn't know this. I didn't know this because I only use Python a little bit here and there. I still stick to my older ones. So if you see, you have memory, which is, if it is not going to come right one after the other, when you want to access elements, you have to go all over the place. It's not efficient. Okay? I didn't know that. That's a great thing. Okay. Yeah. Okay, I haven't used AI, but I have heard that many of the students as well as some of my peers, they use AI if they want syntax. Syntax for, when you program, there is a grammar, right? I don't remember the grammar. What I do will be to Google up a particular, whatever I want to do. Suppose I want to write, say, print or printing into a file or doing one particular optimization. I'll just Google it up. But you could use AI. But I've always used it only at that level because, frankly, I believe that, or maybe this is part of my training that I'm sure I can beat that in some way. I will be able to optimize it in the way I want. Because at the end of the day, my code should be able to do what I want. And I should be able to tweak every part of it. Okay, that's the...
I have one follow-up question, ma'am. Many people say that AI is actually learning like really fast now, ma'am. There's like a really deep learning mechanism. So does that mean that it can actually put out like AI being like what it is, ma'am? Does that mean that they say there are a lot of memes going around that AI can actually build many things beyond human comprehension?
I don't think I have much opinion because I don't believe I've used it that extensively. He has something more to say. Yeah, no, go ahead, please.
What I'd say is because all AI models work only by scraping information that's already available.
I think so too.
But we have a learning mechanism.
Yeah.
The learning mechanism, so it's okay, no, it's fine.
Yeah, I know you will go into a discussion, but I do agree with him in the sense that what happens is with AI, it's just a compendium of information, right? It goes all over and picks up. For example, you can try this simple thing. I'm sure you all have done it, which is put a person's name and ask for something like a resume. You will find that, for example, we did this we did it for fun. My colleague and I was to I had to write a resume for some talk. So instead of spending time doing it, he said, let's use AI and see what happens. So we just put my name and of course it was able to locate me. My spelling is so unique that it was able to locate me. So it located me, but then it said my research was a sum total of everything the department does, which is certainly not true. Then we refined it. Okay, so you refine it by giving more information. Like I, for example, I am a theoretical nuclear physicist. So once I said nuclear physics, I work on neutron star problems. Once you give in little more information, it gave me something which was quite decent, sometimes a little bit more exaggerated. So then you tone it down and make it sound nice. But that's about all the experience I had, and it was for fun. But if you ask me if I would use AI, it would be perhaps for getting a syntax. Or if instead of looking up a book, you see, what we used to do traditionally when I started my PhD was to actually look at a book. But a book may not have everything. Then, of course, now Google or Googling is ubiquitous, and now maybe you will do the same thing with AI. So that I can see. But more than that, I don't even think I use it enough or I feel qualified enough to answer more. Okay? But let's get back to what I was saying here. So basically with this, you can optimize here and there. All right? So how does this 32 distribute itself here? Usually 1 bit goes for the sign. So already you have 31 bits. Now, when you store a number in single precision, which is called real or float in different languages, then you have the exponent, which I call n here, which is what is the exponent? M. Has about 8 bits. So then 8 plus 1 is 9. Subtract it from 32, you have 23 bits left, right? So that goes into the mantissa. Which means the expansion is going to truncate at 1 over 2 power 23. All right? Therefore, this puts a limit on what you can have in the mantissa. You just can't, if you have, for example, numbers which are called machine numbers, which require only finite number of bits, then it's possible that you may store it well within your 23. But if it is not, you have to truncate it. It may be such that it is so small. If it is a small number, then you will try to move as much as possible into the exponent, but the exponent also has a limit. Okay? If it allows only 8 bits, how many numbers can it have? 255, because anyway 1 goes for the sign. Correct? So 255 numbers, it's 2 to the 8 minus 1. 255 numbers is all you can have. So you may say that the exponent itself goes from something like 127 to 128 in terms of numbers, because that adds up to 255. But if I don't want to waste a number for the sign, I'm going to shift this 127 to 0. No, minus 1 for the sign. Sign.
No, but totally
Why?
0 also, right? Minus 1 to minus 127, 127.
But if you have a 0 in your exponent, it's of no use, right? I would like to.
Number 0. Oh,
Ah.
yeah, right.
Why will you want to even store it as a. Yeah. So you won't need it. Correct? So therefore, what you want is to actually store, when you have this, what you want to do is to shift this guy to 0. So you want to have only positive numbers. So you set a bias. Okay, you call this guy 0. So which means you add your 127 there. So that becomes 255. So 0 to 255. Okay. So therefore, now what you do, so with this you can sort of play around with the mantissa with your 8 bits. Okay. And it turns out the smallest number you have is about 10 to the minus some 39 or 40 or something in single precision, or which is float. Now you can, if you change it to double precision, you will get 2 times the word length. If you get 2 times the word length, then this is still, the sign will take 1. This exponent is supposed to have 11. That's again a convention. Then the rest of it, about 52 or something like that, will go to this guy. Okay. No matter what, there is an upper bound on what this I can be. The smallest I that you can, the smallest power of 2 you can have is either 1 over 2 raised to 23 or 1 over 2 raised to 25. All right. So where will this affect you? Because always you can say, well, if I have a small number, I can move things between the exponent and the mantissa and somehow be all right. The answer is yes, it is true. But the problem comes when you manipulate things. For example, suppose I have a number 1 and I want to add to it some quantity. I'm going to call this number epsilon. Okay. So first let me say I take my epsilon as 0.1. All right. Now what I'm going to do, this will give me, of course, if I take epsilon as 0.1, this will give me 1.1. What do I do in the next step? I'm going to divide my epsilon by a factor 2. Maybe even a factor 10. I don't care. I'm going to divide my epsilon, make it smaller, and then add it to 1. If I keep doing that, what happens? Your epsilon becomes smaller and smaller and smaller. And you're adding it to a number which is of natural order, which is 1. So when you do that, how do you manipulate? You always pull out an equal power and then you pull out a common exponent, right? If you have to do the math, you will pull out a common exponent and then you will add it to the number. So you know I should get 1.000000 and then a significant thing. Now if you do this, what happens here? The most significant bit can get flushed out. Correct? It can get completely flushed out because you're not asking if you can store epsilon which is small. Yes, you can store. In fact, it's of order 10 to the minus 40 in single precision. Double precision is 10 to the minus 300. So that's small enough for most of the things we want to do. Okay? But you cannot store anything which is smaller than 1 over, you cannot make a difference to 1 if epsilon becomes smaller than 10 to the minus 7 in single precision. Single precision is when you have it as float, which means you have only 1 word length. Double precision is 64 bits. That's all. Okay. Single precision, and it's about 10 to the minus 15 or 16 if it is double precision. Okay. That's all. So here you have 32 bits and here you have 64 bits for the same thing. But that's all you can ask for. Okay. So therefore, when you have this, which means what? Once you keep making your epsilon smaller and smaller, it will only give you 1 as your answer. Okay. That is the limit of your precision. So which means any answer I get on a computer cannot be more precise than whatever this guy is. So if I use double precision, which is what I will use for scientific computing, I'm not going to get answers which are better than 10 to the minus 15 in a manipulation, because always in a manipulation I'm going to add numbers or multiply numbers. Correct? So there is always some arithmetic operation that happens. These arithmetic operations are going to be limited by this precision. This is called machine precision. I'm going to give this symbol epsilon m. Okay? It comes because what is the smallest power in your mantissa? And in this case, it will be 2 raised to some 52 or something like that. Because really, the choke point is here. Correct? Because you can't do anything, you can't move anything to the exponent because you have something, you're adding it to 1. So that is your problem. All right? Not so much as storing epsilon. Epsilon can be very small, but it will not make any difference when you add to 1. The other problem you have is what is called subtractive cancellation. If I take 2 numbers and subtract them, okay? Of course, if one number is large and the other number is small, their difference is of course going to be the large number, hardly matters. But if I take 2 small numbers and subtract, it is possible the difference is such that it can't be stored anymore. The precision will come. Okay, so therefore, in all of these cases are something one has to worry about when you program. Even something like summing series, okay, you will see that this additive error will kick in if you are summing series. If you are having series with alternating signs, you will have subtractive errors coming in. Okay, so you really have to think about how you program everything. All right. So now what I want to do, as a demonstration, you all haven't studied calculus in school, correct? You have not, but you at least know what a derivative is. Yeah, you know what an integral is. So I'm just going to work with these two as examples of algorithms, okay? And tell you how to track errors and how to actually get some number which is meaningful. This is all my aim is, okay? So remember that there is always something called the machine precision. This is because you only have finite number of bits to store information. That's it. Okay. So now, let us do differentiation. I'm going to take some arbitrary function f of x. I want to find its derivative at this some point x0. How will I do what is the definition of a derivative? It is, so suppose exactly, so if I want, let's say at this point x itself I want to find the derivative, it will be f of x plus h minus f of x divided by h 0. Okay. Now, I am going to show you that this h going to 0 is not possible on a computer. There can't be. Why? There is an upper cap. What do you think is going to come in? If I make h smaller and smaller and smaller. Subtractive cancellation. Forget about it. Look at the numerator. So your numerator will start having junk. It's a limit. Under a limit, your derivative still exists. Otherwise, if it's not defined, then you have a different problem altogether. But I'm saying a function has a derivative at this point x. Okay. So if I look at this, certainly what is going to limit it is this subtractive cancellation. I cannot have anything more than the machine precision. That is the one that's stopping it. All right. So already I know that my h cannot be so small that the difference between them is smaller than the machine precision. That limits the h first. Okay. But then there are other things, and I'm going to tell you that right now. So of course, you can see already the algorithm will improve. Okay. If I have to write an algorithm for it, this will be my algorithm. That's it, f of x plus h minus f of x divided by h, and I'll go on changing h, make it smaller and smaller and smaller. At some point, I'm going to reach machine precision, okay, which is f of x plus h minus f of x cannot be smaller than 10 to the minus 15. That is capped there. If I make h such that this difference is smaller, I'm going to get junk. Okay. So therefore, you see, if I have to see what is the algorithm, what is the error in this algorithm, in this computation, even this simple thing has two contributors for the error. One is the error in the algorithm. What is the error in the algorithm? A finite size of h, because after all I'll start with some finite h and then keep making it small. If h is not small enough, there is an error, and that error will only improve as I make h smaller and smaller. Then there is another contribution, which is round off. That comes. Why does it come? Because this difference cannot be smaller than the machine precision. So this round off is going to be some epsilon m over h. I know how that goes. So now this is the only thing I can play with. I have to improve this. There's always a competition between these two. Okay? So therefore there is always a sweet h which will work and nothing more. Alright, so h cannot be 0. That's the first thing that comes. With what will be its analog in integration? In integration 2, it's an area under the curve. So therefore, between 2 points, if I integrate a function, and let's assume the integral exists and so on and so forth, then what happens? You want to make this slice smaller and smaller and smaller and smaller. You can't do that. So decreasing h equals increasing n. You can't take the limit where the number of integration points go to infinity. It's again limited. Okay, and that's what I want to demonstrate. To do this, maybe before this, let me tell you this algorithm. So, defining f prime of x as f of x plus h minus f of x divided by h, the algorithm has a name. It is called forward difference. This is the algorithm. Okay, this is called forward difference. Similarly, I can do one more. What is it? I can do an f of x minus f of x minus h divided by h. People are very creative. It's called backward difference. Okay, so there is nothing more to this. Now, what is the algorithmic error in this or this? They have to be the same. There's nothing very different about the two. Correct? So let's ask how do I find out the algorithmic error in forward difference? To find the error in the algorithm, I take f of x plus h and do a Taylor series expansion. Okay? If I do an expansion, the first term is f of x plus h f prime of x plus h square by 2 factorial f double prime of x plus etc. Right? Now, f of x, if I subtract, then I am left with h f prime of x plus h by h square by 2 factorial f double prime of x plus etc. Right? Now divide by h. So this guy goes away, this goes away. Okay? So if this is going to be my numerical estimate of f prime, what is the error? A term like h. If I have to bring it to the other side, then I know I'm making an error of order h. Correct? So if f prime of x is defined precisely by this guy, then the error is h. Alright? So therefore, the algorithm will have an error which goes as some constant times h. So this becomes better the smaller the h is. At some point, this will start to dominate. Okay? And that is the same thing you have even in this guy. There is no difference. But I can do something better with a very clever trick. And that trick is the following, which is I have an expansion for f of x, x plus h. Now let me write down the expansion for f of x minus h, which is f of x minus, sorry? Okay. H square over 2 factorial. I want one more term here. So Okay. Now, I want to, what do I want to do? I want to find f prime, so I have to subtract. Correct? I want to find, certainly I want to have f prime. If I add, I'll eliminate the f prime, but I want to subtract so that I eliminate the f of x. Okay? So now, if I do x plus h minus f of x minus h, what do I get? 2h f prime of x plus, then the h square goes away, 2h cube, absolutely, by 3 factorial f triple prime of x. Okay, and then there are higher terms, or all powers will be there, correct? Now I'm going to divide by 2h. If I divide by 2h, so this factor 2 goes, then this becomes h square. And if I use this as my definition for f prime, then what is the error? H square. So a simple trick. I know for doing a derivative, I will need two function evaluation for sure. Now the point where I evaluate these two functions have made all the difference. Okay, if I do this simple thing of forward or backward difference, I will have an algorithmic error of h. Here I have h square, that's much better. Okay, but again, where will the limit? So if it is forward difference or backward difference, it goes as some c times h, otherwise it will be some d times h square. But still the problem will be this guy. So already you see, even in something as trivial as finding the first derivative of a function, you really have to think about how you want to do it. You want to make your algorithm better when you choose a parameter, because all algorithms will be given by a parameter, because it's limited by the fact that this parameter value cannot be arbitrary on a computer. Okay, so therefore this is the best you can do, and already you see for the first derivative you have found an improvement. A second derivative is usually terrible. Second derivative is bad because you have to now do a derivative of this guy, so which means your error is going to build up. So no matter what you do, your errors are going to build up, and you have to find out smarter and smarter ways of coming up with an algorithm. Okay, so now I want to demonstrate precisely what I said, and then I want to get into integrations, because there again there is a very smart method that one uses, okay, which uses a lot of probability. Sorry? Why is that an error? It's not an error. It is because you're approximating, right? See, what is it you want? Normally when you do a derivative, when you set up the first derivative, you'll take h very, very small. If you take your h very small, does any of these terms matter? No. Right? But you cannot take h very small. If you take h very small, f of x plus h and f of x become very close. So you'll start getting nonsense. Right? And I'll show you how you will get this nonsense. Okay? So therefore, whenever you have to, when you keep your h finite, the largest term after you have set up your algorithm is called the truncation error or the algorithm error, because you are truncating. Okay, so this h square is called the algorithm error or a truncation error. There you had an h, that's called the algorithm error or the truncation error. That's just another name, because you're actually truncating something. Okay, if you could take your h as small as you want, there is no error. So that is how h quantifies the error. So h in some sense is a parameter, isn't it? No, it's a quantity that you specify. You specify the quantity, the computer gives you a solution. You take some other h, it gives you another value for the first derivative. The smaller the h, the better is the derivative. But too small an h will allow the other b's to kick up, which is the round off. You will see this now. And that's what I want to show. Okay? And I'm going to take a particular example, which is, I'm going to take f of x to be e to the x. Extremely nice and simple function. There's nothing great about it. But now we can ask with such a function, what happens? Okay? So if I want to find out with forward difference, derivative of e to the x, it's going to be e to the x plus h minus e to the x divided by h. Correct? Therefore, I pull out e to the x. This becomes e to the h minus 1 divided by h. So, really the problem is this guy. The smaller h becomes, the closer e to the h gets to 1. And when it becomes close to 1, you will start getting nonsense results. Okay? So, let's see what happens. You will see what I mean in a minute. I need to now. Why should I call it nonsense? You will see it.
Swayam Prabha. Digital India. Educated India.